Let's begin with the vertical line test. The vertical line test can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph in more than one place, then the graph does not define a function, because a function has only one output value for each input value. Let's see what I mean by this. For example, in which of the following graphs is y a function of x? So looking at that first graph, if I draw a vertical line right here, and again this said drawing any vertical line, you can see this graph intersects, or this line intersects the graph in 3 different places. So since it intersected it at more than one place, we are able to say that this is not a function. But the question is why? Why does that work? Well, when we draw a vertical line, essentially what you're doing is you're going through that specific x value, so x equals 2. So each of these points on the graph have an x value of 2. So that means for that one input value, there's 1, 2, 3 different output values. In order to be a function, you can only have one different output value. If I looked here and drew my vertical line through x equals 0, you can see for x equals 0, it goes to 3 different y values. So that's why this vertical line test works. If I look at the second one, this is a function. And that's because if I draw a vertical line anywhere, I'm only going to intersect this graph in at most one place. And the second one is, or the third one is not a function. Here, if I draw a vertical line in lots of different places on this graph, it's going to intersect it in more than one place. The zeros of a function. The zeros of a function f are the solutions to the equation f of x equals 0. So in other words, they're all of the x values that make the equation equal 0, or all of the x values that have a corresponding y value of 0. The function p is graphed to the right. Determine the following. The zeros of p. So again, I'm figuring out what x values have a y value of 0. Well, y is going to equal 0 on the x-axis. So that means that the zeros are actually the x-intercepts. So this value here, when x equals -3, has a y value of 0. And this value here, when x is 3, has a y value of 0. So the zeros of p are -3 and 3. State the domain of p. So domain are all of the possible input values. So they're all of the values of x that have an actual output or a y value. When I do this from a graph, the easiest way or format to use is interval notation. So let's start out with this graph. So the smallest x value that this function is going to take on is going to be -infinity. And then looking through, it looks like I have no issue. All of these x values have at least one y value that they go to. The only time we might have an issue is at -1. So at -1, this open circle means it's not defined there. However, it is defined at 4. So that x value of -1 does have a y value that it goes to. So I don't have an issue there. Keep on going. All of these x values have y values that they go to all the way down to +infinity. So our domain is all real numbers or from -infinity to infinity. The range. So let's see. The smallest y value. So here's the y values. So the smallest y value this function takes on is going to be -infinity because that's going to go on for forever in that direction. The biggest y value, so it looks like all of these y values have at least one x value that goes to, at least one x value, at least one x value. At 3, we might have an issue because of this open circle, but luckily it has an x value it goes to. So for the domain, all of the y values from -infinity all the way up to 4, including 4, since there's a solid circle there, are included. The y-intercepts of p. So the y-intercept are where we cross the y-axis, so that happens right there. So that occurs at 0, -3. For more information on finding the zeros of a function based on the graph, click on this link.